Hello everyone, it's Paul Bertorelli reporting for AVweb and Aviation Consumer from inside the Lycoming engine factory in Williamsport, Pennsylvania. I first visited this plant about 20 years ago, and back then I couldn't have made this little walk up to the camera because this entire area was wall to wall with hand-operated machine tools, boring machines, lathes, milling machines. All that stuff is mostly gone now, having been displaced by modern computer numerical machinery that's both more efficient and more accurate. And that equipment has almost completely transformed the way Lycoming builds engines. Now we're going to look at that in this video, but first let's examine how the engines themselves get from the parts bin to the test cells. Lycoming has been in Williamsport since the mid-19th century, but it didn't start out building aircraft engines. It began as the Demarest company and manufactured sewing machines. When that market tanked, the company transitioned to automobile engines for a time, like this Auburn Straight 8. Then it branched into aircraft engines during the 1930s. Lycoming built radial engines during World War II and designed the largest piston aircraft engine ever made, the Mammoth 36-cylinder XR 7755, still remembered for shattering neighborhood windows during test runs. But the 1960s put Lycoming on the map with its popular horizontally opposed 4- and 6-cylinder designs, such as the 0235, the 0320, and the 0360 series, still made today for new Skyhawks. At its peak, the plant made as many as 8,000 engines a year. Now it produces an even mix of about 1,500 new engines and an equal number of overhauls. It faces the same manufacturing challenge that competitor Continental Motors does, and that's small volumes of a large variety of engines. To remain profitable, the plant has continuously shrunk its footprint, producing engines from ever less floor space. Here's Mike Everhart.
Lycoming has been in the aviation engine business for 85 years. Over the course of that time, we've accumulated 774 specific type certificates. Because of that, in that time frame, we fielded and are currently in the field almost 200,000 engines. Therefore, at any given time, the requirements and demand from the customer are widely varied. In any low volume mixed model assembly and test operation, you have to be very flexible. So what we've done is we've reduced the inventory in the facility by bringing it to the line. We've refined our forecasting methodologies. We've developed Kanbans in the area based on demand, and we've reduced the footprint and consolidated many other workstations. That's resulted in a reduction in direct labor content and a reduction in inventory and holding costs, as well as a significant reduction in the response time for the customer. So it actually ends up impacting both delivery and cost in a positive way. Well, we have on the assembly floor touchscreen monitors and computers that are tied directly to the engineering database. So as you indicated, you could have 5 unique engines sequentially go through the line. The engine part number is entered in the system, and a unique bill of material and work instructions for each operation is presented to the operator, so he has all the documentation and reference information he needs for that specific engine.
Most of Lycoming's output emerges from this assembly line, which the company calls the legacy line. An engine starts as a partial kit, and as it moves through assembly, common parts are drawn from bins along the line. As do plants in all kinds of manufacturing, Lycoming practices the Japanese lean Kanban style just-in-time inventory. That's a real challenge when the volumes are low and variability is high. Now I did say that most of the old equipment at Lycoming has been removed, but not all of it. This polishing lathe behind me here, circa 1940, is in daily use because it does something the automated equipment can't. But the real story is the investment that Lycoming has had to make in modern equipment. It's really a story of survival. Here's Mike Kraft to tell us about it.
So we're standing in front of the Akuma MA600 Space Center at the plant, which is one of a flexible machining center that we invested in some years ago. A lot of what Lycoming has had to have done in the last few years just to survive and be competitive is to renew our investment in the machinery. And when you take a look at the worldwide competitive nature, you have to invest in some of the best machinery possible to be able to get the productivity out of it and to just enable the plant to continue on. At one time, we were doing a lot of our parts on regular manually controlled machines. hadn't been updated in quite a while. And when you get yourself into that mode in manufacturing, particularly as a manufacturer based in the U.S. competing worldwide with everything from low wage rate states to folks that continue to invest in technology, you can't continue on with that. So we took a number of steps, starting probably 7 to 10 years ago to renew our investment in the plant and bring machines like this Akuma into the plant, which allows us to be competitive with anybody worldwide, and do it in an aviation environment, which is low volume, high mix, very specialized parts. Because in some engines we only make one engine a year of one model type for one customer. And to do that, you got to adapt. And this is a good example of our adaptations that we will now see throughout the plant.
One of the most impressive and surprising machines at Lycoming is a turnkey piston line. It's surprising because most engine makers buy their pistons from vendors, and it's impressive because this array of custom-built machines, designed by the British automotive giant Cosworth, takes the piston from a raw lump of near-net aluminum to a finished part. The only hand operations are a bit of deburring and a careful inspection under a zygo light. And the pistons now get something they never had before, a serial number. That means better parts tracking and improved quality.
So one of the items that this has on quality, these new machines come in with temperature compensation, tool wear compensation. You're going direct geometry models from the CAD side into machining models. All those pieces allow you to achieve better quality not by inspecting the part by you're done, but by building in more robust processes at each step of the manufacturing phase. So when you kind of take this approach and step into the part and every aspect of the part that you're cutting, you end up with better quality as a result of the manufacturing process, not by screening parts at the end of the line.
But that's not to suggest Lycoming doesn't do inspection. It does a lot of inspections. The plant has a complete metallurgical and chem lab, and many of the parts produced by state-of-the-art CNC machinery still get a once-over from temperature-controlled coordinate measuring tools. And for the final quality check, each engine gets a thorough ring-out, one of Lycoming's 16 test cells, before going down the trim line for dressing and final inspection. After that, it's into the box and off to the shipping dock. In a future video, we'll look at Lycoming's new diesel engine project, the DEL 120. Meantime, you can find a full report on Lycoming's reinvestment in the February 2015 issue of Aviation Consumer. I'm Paul Bertorelli reporting. Thanks for watching.